Hello. So, I'm Jacques Pienaar. I'm from the University of Vienna, and I work with Chazza Bruckner and the Bruckner group there. And I'd like to thank RIMS for making it possible for me to be here. And it's pretty exciting to be at QPL and hear all this talk about causality and quantum mechanics. Right? Some exciting things are going to come out in the coming times. So, Reichenbach's common cause principle. What is it? What does it mean? No one really knows. But it seems to be something of an empirical physical principle, something that we observe to be true. As to why this should be the case, well, something of a mystery. And it seems to fail in quantum mechanics, which is something that people are looking at more now as to, does this mean something? It comes in two parts, as Ray mentioned. There's a principle of common cause, so when you have correlated events, there should be a common cause for them. And there's also the factorization principle, which says that the conditional on the common causes, the marginal probabilities of events should factorize. As I said, this just seems to be true empirically of classical systems, and maybe it's true of quantum systems if you formulate it in the right way, maybe not. So to illustrate, suppose that you have a typical Bell scenario, two settings S and T and outcomes A and B, space-like separated. And I've drawn the settings as just circles, and the outcomes are shaded circles to point out that the settings are, think of them like knobs that you twiddle, the experimenters control them. The outcomes are sort of nature's response to that twiddling. And suppose that we see these outcomes are correlated. Well, straight away there's a violation of the principle of common causes, so let's stick in a common cause there to try and explain this. So this is just some third variable, which you might imagine twiddling, say preparing some kind of joint correlated state. And then we can say, well, what kind of statistics would this imply? And classically, we would expect that conditional on knowledge of the settings and this shared resource, we should get factorization. But of course, this being the Bell scenario, we know that if this third variable R represents, say, your setting on the production of an entangled pure state, like a Bell state, the probabilities will not, in general, factorize. So here we have an apparent violation of the factorization part of Reichenbach's principle. And to make this a little more formal, given some kind of graph like the one I've just shown you, we have a graphical criterion, D-separation, which tells you which conditional independencies you should expect. And this embodies that factorization criterion. But maybe, so you'll see there, I've listed for the Bell scenario, the independencies you expect, and all those implied by them. But maybe there's some other graphical criterion which does not produce the statistics expected from Reichenbach, but just produces the statistics you expect from a general quantum network. Can we come up with some other graphical criterion that will tell us what we expect from quantum mechanics? So you can think of this as kind of relaxing Reichenbach's common cause principle to something else that's embodied in this. And that's what we've attempted to do, is come up with some notion of what I call Q separation that gives the right things. You might say, well, maybe this is trivial. As you saw before, there we've just got one extra relationship from the factorization which we want to get rid of in the quantum case for the Bell scenario. But what about more general scenarios? Is it just a matter of going through and chopping out some conditional independence relations? Well, it turns out that there's some really non-trivial structure with in quantum graphs. So for example here, imagine again S and T are settings that you twiddle to produce things that T might be producing an entangled state. Classically, we expect S and B to be independent of each other, conditional on T, and quantumly as well, because S we choose freely independently of what the measurement outcome is on the B side. But, and I'm not sure how easily I could give you an intuition for this, in quantum mechanics, if we then condition on A, this is no longer true, whereas classically it would be. So conditional on A and T, S and B are no longer independent in quantum mechanics, whereas classically they would be. And so Yes, that's it. I'm done. Thanks.
Thank you. Question, comments? Bob?
Is this one of the semi-graphoid actions that fails?
Again?
Is this one of the semi-graphoid actions that fails?
No, all of the semi-graphoid axioms are satisfied. It's just the d-separation rules fail, basically.
Do you have an inequality that violates it?
No, but, well, actually, yes, it would be Bell's inequality. So I think if Bell's inequality were satisfied in this case, then you would find agreement between classical and quantum. But I think it's specifically when there's entanglement, when T represents the production of an entangled Bell state, and the measurements are in, one of them's in diagonal basis from the other one, then you'll see that conditional on A and T, S and B become correlated.
Next speaker again.